everybody, and thank you for tuning in to this talk. My name is Miro Cupak, and I'm with a Toronto-based company called DNA Stack. Our mission at DNA Stack is to improve lives of people affected by genetic disease, and we do it by making standards and technologies for discovery, sharing, and analysis of biomedical data. If health tech is something you're interested in or curious about, feel free to reach out to me. I'm very passionate about this topic and always happy to connect and talk about it. If you want to reach out, here's my Twitter handle in the corner here. In this session, we're not focusing on the healthcare domain. We're focusing on the underlying technology stack, which in our case is, of course, Java. In particular, we're talking about what APIs and constructs Java provides for concurrency, how the concurrency model has evolved over time, and what the next step in this evolution is. One thing I find about concurrency is that whenever it's talked about, the concept and the theory behind it is really the topic of the conversation. Critical sections, thread safety, Java memory model, concurrency versus parallelism, that sort of thing. But as a developer, I just want to dive in. I want to know what the APIs are and how do I actually use the constructs in my code. So today, we're going to take a very pragmatic approach to concurrency. In fact, to the level that I've actually only prepared 2 slides for you, and you're looking at one of them. I like learning through examples, so the rest of this talk is going to be all live coding. I'm going to write my examples in JShell because I find it's nicer for demonstrating sort of isolated things when you abstract away from all the magic ideas do for us. So let me switch to my terminal here and let's get started. The basic unit of concurrency in Java is a thread, represented by the thread class. Interestingly enough, this is something that has been available since the very first version of Java. Even in Java 1, 25 years ago, we had the runnable interface and its implementation thread. So we could easily do something like this. I'm just going to start by declaring my task as runnable. Let's just do a quick lambda here. Of course, lambdas weren't available at the time, but we can take advantage of them now. And I'll just do a simple printout here. Let's say hello Devoxx, and that should be it. And now I can create a thread, and this, of course, takes a runnable. So I'll just give it my runnable from before, and let's call this T. And finally, I should be able to start the thread, and we can see the right output. And that's very nice. This was a big deal at the time, because now we had this abstraction in the JDK, so we no longer had to write native code to handle threads. And JDK 1 was tiny. We're really talking 200 classes or so. And a big chunk of that was actually AWT and its UI components. Java Lang was only about 20 classes at the time, plus some errors and exceptions. So the fact that the thread was present in the very first edition of Java really shows you how core the concept is to the Java platform. And a lot of our stuff really is tied to threads. At the VM level, we have exceptions where the context is given through the thread's stack trace. Debugging is also done through thread, and profilers group data by threads. So what could we do with this construct in the early days of Java? Well, not much, actually. If we take a look at the API here, we can see that there are a few methods here, and most of these have been here since the early days. But it's quite a strange API because different parts of it withstood the test of time to varying degrees. Some parts are not deprecated, and others are confusing. So what do we actually have here? Well, we saw the start method in action, which is sort of the main method you would want to call here. Another really commonly used method is the method currentThread, which, as the name suggests, gives you the reference to the thread that you're currently in. So I can, for example, do something like this, thread currentThread, and let's call this T. And now I can use any range of methods that allow me to extract some information about the thread. And of course, the most well-known one, and the one we've all used before, is getStackTrace. So this, of course, returns an array of stack trace elements representing the stack of this thread at this time. And like we said, exceptions and debugging context is all tied to a thread. There's also a method called getID, which, as you would expect, returns the identifier of the thread. Threads in our application are actually numbered sequentially by the JVM. That's why the ID on the main thread is 1. We also have a method called getName, which actually returns the name of the thread. In this case, we're just in the main thread. But this implies that we can actually name our threads, which can be handy if we have many of them. And this is quite an underrated feature, which I wish people used more often. It's very useful for logging and debugging purposes. Actually, not only we can name threads, but every thread has a name. If we don't specify one, it will be generated for us. And the easiest way to specify one is through the constructor. If I try to create a new thread here, let's make a new runnable now, and I'm going to print out the name of the thread. So thread currentThread getName. And let's close everything, and let's call this T. Now let me add the name for my thread here. Let's call this worker, and now if I start the thread, you can see that we see the name, and the name indeed is a worker. So we saw that you can start a thread using the method start, right? But confusingly enough, there's actually another method here which looks like it might start the thread, but it does something completely different. And that method is run. And you can see that if we try to call it, it actually gives us a different result. Because you see, this is the run method from the runnable interface, and if we call it, it doesn't actually start a new thread to execute this runnable. This is just a normal method call now. So the thread executing this is, as we can see, our main thread. So if you call run by mistake, it can be quite tricky to hunt down the bug. Start is the method you're most likely looking for here. There's actually a similarly confusing situation when it comes to stopping a thread as well. You might be tempted to just call thread stop, but this method is actually deprecated and just inherently unsafe. The closest thing that we have to stopping the thread is the method interrupt, which is not completely the same thing. Interrupt is sort of a polite version of stopping the thread. Essentially, you're asking a thread to stop, but it's up to that thread to decide what it really wants to do. But this is what we have in the JDK right now. A similar situation is in place for pausing as well. I'm sure we're all familiar with thread sleep as kind of the main pause method. Let's say I just put this thread to sleep for 2 seconds. This, of course, works just fine. But for example, the method suspend or its counterpart, method resume, they're both deprecated and should not be used. There is actually one more thing. We've covered what you can do with individual threads, but if you have many of them, you might benefit from a construct simplifying thread management, like a thread group. Thread groups, as the name suggests, provide a simple way of grouping threads. So you can create a new group and you can name it. Let's just create a new group called group, and let's call this TG. And that's pretty much it. That's more or less all you can do with it. The API is actually very simple and not a lot of things going on here. One thing to note here maybe is that we don't actually have methods on the group for adding or removing members. To add a thread to the group, you need to specify the group when you create a thread. So if I go back to my constructor maybe from before, which was this one, I can now add the notion of the group here. And now if I take a look at the group, you can see that it indeed is the group that I just created. There's a reason why we add threads to groups this way. Group assignment is permanent. You can't just move threads between groups. And actually, every thread needs to be assigned to a group. If you don't name one, you get assigned to a default one. So there's a group called system for the JVM threads, like system threads, and it has a child group called main for our application, which starts with a single thread running our main method. We can actually even see it in JShell here. If I obtain the reference to my thread and take a look at the thread group, you can see that it indeed is the group main. And this is actually a hierarchy. Thread groups are also assigned to other thread groups, so we sort of end up with this tree of threads. And this is a useful, basic thread management construct. Now, I want to mention one more thing here, which was actually added in Java 2, but then really became useful in Java 5 with the addition of generics. And I want to mention this because it's one of the most widely used concepts related to threads today. And that concept is, of course, thread local. As we started relying on threads more heavily, it became pretty clear that we needed a way to store data in the scope of a single thread, which is a use case not really captured by other Java primitives. And thread local is the construct that allows us to scope variables that way. So unlike regular variables, thread locals allow us to give each thread its own independently initialized copy of a variable. So it's a perfect feature for storing thread state. It's actually really simple to use. We have a class called thread local, which only has a handful of methods. So we can, for example, create a new thread local. Let's say thread local of type string, and then let's call this TL. I can set its value, importantly, for the current thread. So I can use my favorite string here, hello Devoxx, and then of course we have a get method to extract the value. And that's pretty much it. It's actually pretty much all there is to know about threads in general, as we've had them in Java for about 25 years. As far as concurrency constructs go, threads are actually very easy to understand. We've spent about, a few minutes going over them. And we saw the usage was pretty straightforward. When we use threads this way, we do synchronous programming, right? Every task executes start to finish on a single thread. And we saw that from code perspective, this was easy to read, fits well with the design of the language, as well as the tooling. OpenJDK currently provides a single implementation of threads, which is a relatively thin wrapper around operating system threads. So when you create a thread in Java, a new operating system thread is created to back it. And this gave us simplicity, but as you can imagine, it results in certain inefficiencies. The operating system, for example, doesn't know what kind of workload the thread is executing, or what language it's written in, and how the language manages the stack. So the operating system must go for a very conservative and robust approach that gives us good compromise across all the possible implementations, which in turn makes Java threads pretty heavyweight. Scheduling is also a compromise across all the use cases, so you're not getting optimal cache locality, and context switching needs to go through the kernel, which is also relatively slow. And because any thread wraps an operating system thread, and that thread is costly, we can't have many Java threads at the same time. And because every task consumes a thread, the number of tasks that we can handle is bound by the number of threads that we can handle, which on a regular machine, even nowadays, will be somewhere in the thousands. So threads themselves became the bottleneck. And there's certain irony in that, right? The reason threads were introduced in the first place was because hardware was the scarce resource, and threads were the lightweight mechanism at the time allowing us to share this scarce resource. Yet over time, threads themselves have become the scarce resource, and soon we needed another abstraction. So what did we do? Well, the same thing we always do when we have an expensive resource. We try to share it. And how do we share threads? Thread pools, which brings us to Java 5. The idea with thread pools is that instead of spawning a new thread for every incoming request, we have a pool of threads. We typically create such pool at the start of the application. When a request arrives, we borrow a thread from the pool, we run the task on it, and then return the thread back to the pool when we're done, which gives us some level of sharing. Java 5 introduced 3 useful interfaces in this aspect. It introduced Thread Factory, Executor, and Executor Service. Thread Factory is probably pretty much what you would expect. It's an implementation of a very common design pattern in Java. It's a low-level thread management construct. It's basically an object that allows us to create many threads of certain configuration on demand. As a simple example, I'll just use the default thread factory here. I'm going to reach into executors, obtain the default thread factory, and let's call this TF. And now I can use this factory to create a new thread, which unsurprisingly needs a runnable, so I can just reuse the one that I had from before. And I can also immediately start it, and you can see that this gives the right result. So that's thread factory. Executor is an object that executes tasks, so runnables. It's a way of decoupling task submission from thread use and how each task will be run, so scheduling. It's a higher level construct than a thread factory. It's something that will actually typically use a thread factory to deal with threads. And this is what you would normally use instead of thread factory directly. We also have Executor Services. Executor Service actually extends Executor, so it's essentially a more extensive framework for execution of tasks, or runnables. All the implementations of the Executor interface in the JDK actually also implement Executor Service. So Executor Service is the more useful construct here. And in practice, this is what we really mean when we're talking thread pools. So how do you use this? Well, I can create a new Executor Service, let's say by reaching into executors, and let's just create a fixed thread pool, let's say consisting of 3 threads, and let's call this E. Now, I can call the method execute here, which is actually a method from the executor interface inherited in Executor Service, and in fact, it's the only method in the executor interface. And I can give it my runnable from before, and you can see that this works just fine. And this gives us a lot, right? We've pushed scalability further. We can now relatively easily reuse threads. But this isn't really how threads were meant to be used. This is basically a workaround for improving concurrency. So what are the problems that we might encounter as a result of this? Well, we saw that thread locals are an important construct with threads. And with thread pools, our thread locals might leak. So let's say one of our tasks takes a thread, it creates a thread local, and then forgets to reset it. Then a different task gets the same thread and can now read those unrelated thread locals, which can cause surprising consequences in highly concurrent applications. So it's a good practice to reset thread locals yourself before and after execution. We also saw the methods for interrupting a thread, and we can now encounter synchronization issues with interrupts. Let's say we have a task that's been running for too long for whatever reason, and we want to cancel it. To do that, we need to interrupt the thread it's been running on. But because threads can now be shared, maybe you trigger the interrupt, but by the time it's in effect, the task has already finished, and the thread is now running a different task, and you interrupt that one. And that's something you, as an application developer, need to think about. There are complexities with interrupts that are not covered by abstractions in the JDK. And finally, thread pools are still not efficient enough. Even though we use a pool, we run tasks start to finish on a single thread. So the number of tasks we can run in parallel is still bounded by the number of threads we can handle, which, as we've already established, is not high enough. So how do we push scalability even further? Well, we notice that while a task is being processed, it's only actually performing computation on a CPU for a relatively small amount of time. A lot of its time is actually spent waiting for I/O. So what if, while we wait, we return the thread to the pool, and a different task can reuse it before our task is actually terminated? And that allows us to have more active tasks than threads, which brings us to asynchronous programming. Java 5 took the first step towards asynchronous programming. Together with executors and executor services, which we've seen already, it introduced two other very useful interfaces, a callable and a future. Callable is kind of like a runnable, which we've seen already, in that it's a representation of a task, but it's a task that returns a result and may throw an exception. And while runnables can be run with threads directly, callables can only be run with executor services. And future is simply future result of an asynchronous computation. And this is how they work together with executor service. I'm going to reuse the executor service I had from before to submit a task, which is a callable. So let's just call submit, and I'm going to do a quick lambda here for a quick callable, maybe just something like this. And this, as we can see, returns a future. Let's call it f. And you can see that the method returns immediately, and the future is not completed because it's asynchronous. Of course, it completes very quickly. It's a very simple lambda. So if we take a look now, you can see that this feature is now completed. And if we try to extract the value, you can see that it is actually the value that we would expect. And this seems simple, but it actually gives us a pretty sophisticated asynchronous system and allows us to push concurrency in Java a bit further. But as you can imagine, as time went on, this still wasn't efficient enough. Pretty soon we needed more. And the help came with Java 7, which introduced the fork join framework, and most importantly, fork join pool. Fork join pool implements executor service, so it's a thread pool. And it's an ideal candidate for writing asynchronous systems, because it understands that some tasks need to wait for others. It avoids changing threads, if possible, until workload is significant, so it can help prevent cache corruption. And it basically provides better utilization of resources and generally better performance for asynchronous processing. So how does it do it? Well, the key assumption behind it is that newly created tasks are more likely to have their data in a closer cache than older tasks. So maybe we should run those on our CPU and schedule the old ones for other CPUs. So this is how it works. When I create a task, it goes in the queue. Every thread has a queue it needs to do. When the thread is ready, it says, hey, I'm ready, do we have any tasks in the queue? And it takes the task and executes it. When a task needs to do more work, it adds more tasks to the local thread queue. So the thread keeps pulling tasks from its local queue, which means ideally we're not corrupting our cache. So how do we scale this across threads? Well, if another thread is out of tasks, it does what's called work stealing, where it grabs a task from the bottom of someone else's queue. So the expectation is that the bottom of the queue is far enough from the cache that moving it to a different CPU will have the least performance impact. And it turns out that this works really well for asynchronous computations. We get good single-threaded performance, and as we're adding tasks, we get pretty good sharing across CPUs. In fact, fork join pool works so well that it is what pretty much all higher-level components relevant for concurrency in the JDK use under the hood nowadays. If we wanted to use it directly, a very simple way of doing that would be just by modifying the example that we had from before, where I was creating an executor service, and now I can create one like this. I'll just reach into the fork join pool, and let's just use the common pool here. And now I can repeat the steps from before. I can use this executor service to submit a task, and of course, I can use the get method to extract the result, and you can see that this works just fine. This is, of course, a very primitive way of using the fork join pool. I'm not really benefiting from it here, but it's just for demonstration purposes. So with futures, we're asynchronous. With the fork join pool, we can do synchronous very effectively. But as you can imagine, time went by and we needed to scale more and more, and at some point, this again wasn't enough anymore. So we took a look at this framework and thought, okay, what are the issues here? Where could we possibly optimize even more? And the problems that we have right now are that futures are hard to compose. What you see in practice when people are using futures, when they try to coordinate multiple tasks, they often do it by essentially performing busy waiting. So you're kind of iterating over your tasks, checking if they're done, and then when the tasks are finally done, you schedule the next task that depends on them, which obviously wastes resources and it makes you block on your main thread. The get method that we had to call to get the value from the future is actually also a blocking call. So I can run things asynchronously, but to get the result, I need to block. To improve, we want to avoid blocking threads, we want to optimize our use of CPU, and we want to avoid changing threads, because context switching is expensive, and the thread we switch to generally uses different data from the previous thread, so the CPU needs to pull in the data, and we want to optimize our use of cache. But as it turns out, Java 8 helps us with this quite a lot by introducing completablefuture. Completablefuture is basically a framework for primarily non-blocking asynchronous programming in Java. It's built around a class called completablefuture, which, as the name suggests, is a future that may be explicitly completed, so it can set its value and status. And when I say it's a future, I mean the class literally implements the future interface we've just seen. But it actually extends its functionality significantly by implementing another interface called completion stage, which was also introduced in Java 8. Completion stage is a representation of a stage in a larger computation. So basically, we use completable futures to model tasks in a bigger, primarily asynchronous workflow, and we have APIs to create dependencies between the tasks and chaining them. In other words, completable future addresses several problems that we have with futures. It makes tasks easy to compose, and it allows us to do so in a non-blocking way. And it automatically uses the fork join pull behind the scenes, so it actually performs very well. So this is a very mature framework for synchronous programming, but this comes at a cost of complexity. And this cost is substantial. If we wanted to show all the functionality this framework offers and common usage patterns, this talk would be several hours long. In fact, just taking a look at the API, you can probably tell this is noticeably more complex than anything we've seen today during the talk. If I just create a new completable future here and take a look at the methods, you can see that there is a bunch of them. Completable future is a big class, almost 3,000 lines of code, and quite a few methods, and if I remember correctly, there are over 80 public methods on this class alone, with inheritance and overloading. A few of them come from the future interface, as we've seen, but the main API comes from the completion stage interface, which has over 40 methods. So yeah, probably not the best API design, but there is a system to these. The reason we have so many methods is because there are 3 categories of what we want to express in the API, and we need to express all the possible combinations, which gives us 36 methods. The 3 categories are what kind of a task it is, how do I process it, what kind of an operation it supports, and where, what thread can it execute on. As for the task, there are 3 types. It can be a runnable, it can be a consumer, or it can be a function. As for the operation, we can chain them, so execute one after another. We can compose them, as in function composition, or we can combine 2 of them using AND or OR. And as for the thread it can run in the same executor as the caller, it can run in the new executor passed as a parameter, and it can run in the common fork join pool. So let's take an example. And the simplest usage pattern that I can think of is asynchronous sequencing, which is about creating that basic dependency, ensuring that one task runs after another. So I'm going to create a small asynchronous pipeline here. I'm going to start by creating a completable future in a different way, asynchronously. And I'm going to use supply async here, which takes a supplier. So let's just say, okay, quick lambda here. Let's say hello. And then I'm going to call another method, then apply async. So you're probably noticing the naming patterns here, and the name really tells me, all the 3 things that are being combined in this particular instance. So supply async tells me that I'm going to need a supplier to generate my task, and I'm going to do it asynchronously, so not in the caller's thread, but either in an executor given as a parameter, or I will let the fork join pool decide. Then apply async tells me that the operation is basic chaining. Apply tells me that the task is a function, and async we've already discussed. I'll just use the fork join pool. So this needs a function here, so let's just create a quick one with a lambda. Let's just take the output of the previous completable future and combine it with another string. Let's say hello Devoxx, and then finally I'm going to call then accept async, which again the name gives me all the information that I need. It basically says, okay, the method is again chaining because then it expects a consumer as the type of my task because accept, and again I'm running it asynchronously because async. So I'll just give it a quick consumer here, maybe just a quick method reference, and just like this, and we can see that we do get the right result. So you understand now what the system is, and why we have so many methods, and how the naming works. It also shows a key property of the completablefuture API. Almost anything that you do to a completablefuture produces another completablefuture, which gives us this sort of fluent functional API to model our workflows. Completable futures get us very far, and they address a bunch of issues that we have with futures. We can compose them easily, and we don't have to log on the main thread to coordinate. We can just tell it to run a dependent task when our task is done. This is a very important construct in the JDK that everybody should know about. This is the way to do asynchronous in Java. But like I said, it comes at a cost, and the cost is not low. You can see that even with such a simple example, the API is quite complex. The code is relatively hard to read, write, and maintain. Ordinary threading and APIs we were used to no longer work here, right? We need to use these new APIs. There's also loss of context. We're obviously using threads in the background, but they're hidden from us. We no longer have associations between tasks and threads. To get the efficiency, we split our tasks into smaller stages, and there are no guarantees that different stages of our task continue on the same thread, which of course increases complexity. And this lost context is a real issue, because as we said at the beginning, Java depends on this context, right? When we get an exception, we're given context through stack trace tied to a thread. So now we're only seeing stuff relevant to our stage rather than the whole task. Similarly, debugging is tied to a thread. When we go to the next step, it's the next step for the thread, which might now be a different task. Profiling is hard because it can tell us about the thread pool and that sort of thing, but we have limited information about the running tasks if they're waiting. And if some interesting event happened, we might not know what task it was coming from. So it's tricky. As developers, we're faced with a choice. We can either go for synchronous, which is easy for us, but inefficient for the hardware, or we can go for asynchronous, which allows us to utilize the hardware better, but at the cost of complexity in our application. So how do we solve this? Well, if you think about it, threads is what we like, right? The rest, like thread pools and asynchronous, are basically workarounds to extract more performance from threads. What if we could code in a synchronous way though, but get the scalability of asynchronous? In other words, what if we could lower the cost of threads to a point that we could have so many of them that they're no longer a scarce resource, and we don't need these workarounds anymore? And that's exactly what Project Loom brings to the table. Project Loom is experimental, but a very, very high impact effort, which will quite substantially change how we do concurrency in Java. It's a Java effort, but it's not in the JDK yet. It isn't even planned for any soonish release as far as I know, but it is under heavy development, and it has been under development since 2017. And really things are being changed all the time. The information that's out there often gets out of date pretty quickly, but here's what we know right now. Project Loom really took a step back and said, okay, concurrency has gotten pretty hard, as we've seen today. Let's get back to the roots. Let's take a look at threads and create a much more efficient version of them so that we don't need these complex workarounds like thread pools and futures. Project Loom does this by introducing the concept of virtual threads, formerly known as fibers. Virtual threads are lightweight threads which are inexpensive to create and block. They are managed by the Java runtime and implemented in user space, unlike regular threads which wrap operating system threads. So what you're getting by having Java manage them is a lot of efficiency thanks to the additional knowledge that Java has. For the operating system, as we said before, a thread is more of a black box. The OS doesn't know what kind of workload the thread is executing, what language it's written in, and how that language manages the stack, so the operating system must go for a very conservative and robust approach that gives us a good compromise across all the possible implementations. But if Java manages its own threads, it knows a lot more about what they do, so it can represent them in a much more compact way and adjust the scheduling accordingly. So virtual threads are not wrappers around operating system threads. They're just Java entities. So how do we use these virtual threads? Well, pretty much like regular threads. Compatibility was a big design goal with Project Loom, so tools and libraries that can use threads will be able to use virtual threads as well. There aren't many new concepts, it's more about having new conventions for using concepts that we're already familiar with. So let's take a look at that. Let's review what we've covered today, but do the examples with virtual threads instead of regular ones now. Virtual threads are threads, so to create one, I'll start with a thread class. Unlike regular threads, there is no public or protected constructor for virtual threads by design, so as not to have to deal with subclasses. Subclasses of thread cannot be virtual. So instead, I'm going to call a method here, and that method is called startVirtualThread, which, as you would expect, requires a runnable, so I can just give it the one that I had from before. And you can see that this created and executed a virtual thread, and we got the right output here. We don't have to start threads directly, like we did just now. If we want more flexibility, there's actually a builder. So I can call the builder here. I can tell it to build virtual threads. I can give it a task, such as my runnable from before, and then I can call build, and let's call this T. And now we can check if this indeed is a virtual thread, and of course it is, and we can start it explicitly, and this works just fine. This builder is actually a really nice addition to the Thread API. It's not specific to virtual threads, of course. I can use it with regular threads as well. It's just kind of an overall convenience feature that just happened to be added as part of Project Loom. The things I had to do with threads through constructors and setters before, I can now do with the builder. For example, I can just go back here and maybe I can decide to name a thread, let's say worker, which works just fine with virtual threads as well, and could be very useful actually since we now have so many of them. But there are many limitations as well. For example, priorities are ignored. If I wanted to specify a priority here, I can just go here, priority, and let's say maybe thread minimum priority. By the way this works is the default priority is normal, which is actually just 5. Usually assigned priority on a scale 1 to 10 here. And in this case, I've assigned 1, the minimum priority. But if we do a test, if we take a look at the priority of this thread and see if this is equal to the normal priority, not the minimum one that I assigned, you can see that this test passed. In other words, the priority of virtual thread is always normal priority. Thread groups are not supported either. If I go back to my example here, and maybe let's just change this line to specify a group, I can reuse the group from before, you can see this will not, in fact, work. To be exact, when I say thread groups are not supported, what I mean is that I cannot specify a custom group. But to be consistent with regular threads, where each of them needs to be assigned to a group, they do actually have an implicit group. And if I take a look here, you can see that there is a group called virtual threads. It's pretty limited. The expectation is that we'll have millions of virtual threads. So you can't, for example, even enumerate threads in a group, but it does exist. Many methods that we've seen in the Thread API are also missing support, especially the ones that we've described as confusing. For example, the method run here actually doesn't do anything, just to avoid confusion. The deprecated methods like stop, suspend, resume also don't work, and they actually simply throw an unsupported operation exception. But the main methods that we saw, like getStackTrace, sleep, current thread, and things like that, they of course work just fine. We can maybe demonstrate just one of them here. I'm going to change the task here, do a quick lambda, and maybe let's just print out the name of the current thread. So I'll use the current thread here and then get name. And of course I have to remove this group here, but we can see that this works just fine. Importantly, thread locals are supported as well. These are obviously used very frequently, so if they weren't supported, it would be a substantial barrier in adoption. And we can demonstrate this just by going back to the builder, and I can change my task again. And maybe I'll just modify this to be a block. Let's just do a quick lambda, and inside this block, I'm just going to create a new thread local, let's say of type string. Let's call it TL, and new thread local, just with a quick diamond here. And then let's assign the value here, maybe hello Devoxx, of course, our favorite string. Let's close everything and see if this works. So now if I start a thread, this actually works just fine. The good thing about this is that in some way, thread locals actually work better with virtual threads than they do with regular threads. Because remember, one issue that we had with thread pools was basically the potential for thread locals to leak because we were sharing threads, which is no longer an issue here because virtual threads are so cheap, we don't actually need to share them. There are complications here as well, though. The reason Loom works is because virtual threads are so lightweight, right? To a point that having thread locals could actually substantially increase their footprint. And because we have so many of them, reduce the scalability as a result. So if you actually wanted to keep them really light, you can disallow thread locals through the builder here. If I go back here, I can add another method here, just disallow thread locals. And now if I go back and start a thread, I am actually getting an exception here. It should also be noted that inheritance is tricky as well with thread locals. Thread locals can be inherited between the parent and the child threads. And with Loom, we're actually encouraging creating new child threads frequently for various stages of our computation because they're so cheap. Like we could, for example, create a new thread for each HTTP request to different microservices that participate in answering kind of, one external request coming in. So we might actually rely on inheritance even more now. But thread locals are immutable, as we've seen. And as such, they're not safe to share between threads. So they must be copied when you're creating a new thread, which creates performance overhead. Again, multiplied by the very large number of threads that we have now. So alternatives to thread locals are actually being explored as part of Project Loom. And one of these alternatives are scope variables. Scope variables are immutable, and they have a smaller scope, just a code block instead of the whole thread. These scope variables have been prototyped in Project Loom, but it's a very early prototype. There's just one class with absolutely no Java doc. So it's likely to change, possibly even disappear, or the implementation might even be deferred to a future Loom release, not the initial one. But a simple example would be something like this. I can create a new scope variable here, let's say, for type, maybe let's just use string here, and let's call this s. Now I can bind a value to this variable. Let's of course use our favorite string here. And now this value is in effect for the duration of the scope. So this is still immutable. I can't mutate this scope variable, but I can bind a different value to it in a different scope. And once you leave the different scope, you have the old value again. So I could, for example, have a block in a thread, defining the scope, then create a new thread in that block, share the value in the scope with that thread. It supports nesting that way. And then bind it to something else in the child thread, and then when I return to the parent, it will have the original value. There are some language changes necessary to demonstrate this behavior in a meaningful way, so I'm not going to show it. But for now, I can just simply extract the value so that we can just see the API. What's also important is that not just the bare thread, but Java 5 features that we saw are supported as well, to an extent. So, for example, thread factories work just fine. In fact, they're not only supported, but it's actually much easier to create them now with the new builder. So if I go back to my builder here, I can just tell it, to build virtual threads, and then I can tell it to create a factory, and let's call this TF, and this, of course, works just fine. The importance of this being supported is that this is sort of an integration point with other APIs we're now used to using, such as Executor Services. If you take a look at the factory methods for executors here, pretty much all of them actually accept a thread factory as an optional argument. So you can give them a factory to create their threads, and because we now have a factory for virtual threads, they all automatically work with virtual threads. So you can migrate from regular to virtual relatively easily. I can reproduce our executor service example from before, in fact, now with virtual threads. If I just go to my executor service, and let's see if we can find it, I'm just going to use new thread executor. Let's just use the basic one. And let's say I'm going to pass it my thread factory to make it work with virtual threads. Then I can submit the task, of course, a callable here. So just the quick lambda, hello Devoxx, and this of course returns a future, and now finally I should be able to extract the value from my future. Notice that this really is the same as the example from before, right? The only difference is the thread factory here, so very easy drop and replace. For convenience, we actually also have a new executor directly contributed by Project Loom. If I go back to this line here, I can, instead of the new thread executor, just use the new virtual thread executor, and then everything is going to work as before. This virtual thread executor is actually very simple, since with virtual threads we don't typically need any sophisticated constructs like thread pools because they're so cheap. It actually just creates a new virtual thread for each task. Loom actually provided another enhancement to Executor Services that's very cool. Executor Service now extends auto-closable. Pretty much all the constructs that represent external resources do that in the JDK now, so this just makes complete sense. The advantage in practice is that we can now use Executor Services in try with resources statements. So relying on our example from before, I can do something like this. I'm going to start new try with resources. I'm going to create a new Executor Service. Maybe let's just use the default one with our custom virtual thread factory. And then I'm going to start the body and just submit a couple of tasks. Maybe let's just submit a runnable from before. Let's do a couple of these, just like this. And this, of course, works just fine. So what this does, it creates a new executor using our thread factory. This executor creates a new virtual thread for each task we give it, no pooling or anything because we're talking virtual threads. And then we give it 2 tasks to execute, and when they're done, we clean up. The interesting thing about this is that the current thread will block, waiting for all the tasks and their threads to finish. In other words, when we exit the tribe of resources, all the tasks and their threads are guaranteed to have completed. And this is a very interesting and a very powerful invariant. This concept is known as structured concurrency. And there's literature available about this. I'm not going to go into too much detail. But basically, structured concurrency means that the runtime behavior mirrors the structure of the code, which makes it easier for us to reason about the code. Our code is arranged in blocks, and based on these code blocks, we can see where each thread starts and finishes. So implicitly, every thread has a parent that blocks until the children terminate. There are actually more similarities between virtual threads and asynchronous programming with completable futures, including scheduling. With virtual threads, we're not scheduling on the CPU directly, but we schedule virtual threads onto regular platform threads, which we call carrier threads. So like with asynchronous programming, we do end up scheduling kernel threads ultimately, but we abstract that through familiar threads rather than some new constructs. From application perspective, carriers are isolated, we can't access them. For example, the current thread method will refer to our virtual thread, not the carrier. Only the scheduler interacts with the carriers and mounts virtual threads onto them. Similarly to completable futures, the default scheduler that we use here is the fork join pool, like we've seen before. By default, the number of carriers is equal to the number of cores on the machine, but it is configurable at the JVM level through a flag, similarly to how we would configure parallelization for, let's say, parallel streams. If you wanted to specify a custom scheduler, you can specify it when you create a thread in the builder. So if I go back to my builder here, let's just find one, maybe this one, I can go to virtual and try to autocomplete, and you can see that this does actually optionally take an executor. So for example, if you're not happy with the global number of carriers, you could implement custom schedulers that delegate to different numbers of carriers based on the tasks. As we've seen, executor is a very simple interface. It only prescribes one method, execute, which takes a runnable. There's even an interface extending runnable to represent a task for a virtual thread, and that's called virtual thread task here. This allows us to distinguish between virtual and regular tasks so that we can deal with blocking and resuming on carriers. By the way, the assignment of scheduler to a thread is permanent, so you can't change schedulers for existing threads. One final thing before we wrap up here, Loom also introduces the concept of continuations. Strictly speaking, this is a low-level construct that we as application developers don't even need to be aware of, but it is currently a part of the public API, so I wanted to mention it at least briefly for completeness. The idea is that running virtual threads requires 2 things, a scheduler and continuations. The scheduler decides when and where we run, which carrier thread we mount onto, and the continuation decides what we run. It's a representation of computation that can be paused and resumed. So it's basically a wrapper of a runnable that can pause and continue from where it was paused. With Loom, we're mapping a large number of virtual threads onto a small number of carrier threads. So it works well when threads are waiting most of the time for I/O, which is a common workload in most applications, fortunately. So we need the thread to tell us when it's about to block so that we can offload it and then resume. And with millions of threads, we basically shuffle the virtual threads across the carriers frequently. And that's what the continuation provides, is this ability to pause and resume. So our execution is this constant handoff between the scheduler and continuations, right? And it's important to keep these concepts separate because this allows us to reuse ordinary Java schedulers for virtual threads, as we've seen. Continuation needs 2 things. It needs a scope and it needs something to run in the form of a runnable, of course. It provides 2 important methods. There's a method called run and a method called yield. When you call run, a continuation starts running the runnable until it calls yield. When the continuation calls yield, the run method returns to the caller. And the next time you call the run method, it will continue from the last point the continuation yielded. For example, let's start by creating a scope. I'm just going to create a new continuation scope. Let's just call it scope, and let's call this whole thing CS. And now I can create a new continuation. You can see here that this needs a scope and it needs a runnable. So I give it the scope that I just created. And let's create a new runnable here. Let's create a more complex one. It's going to be a multi-line lambda here. And first, I'm going to just print out something. System out print line, let's say hello. Then I'm going to call yield, continuation yield, to my original scope. By the way, you can yield from any depth here. And then I'm going to continue executing something. So maybe just another printout, let's just say Devoxx here. And now I should be able to run this. So let's actually give this a name. Let's call this C so that I can call run here. And you can see that it did execute the first printout, but then it stopped, right? It yielded and it returned to the caller. We can check if this continuation is done, and you can see that it's not done, still more work left to do. So we can try running it again, and you can see that it now did not execute the first printout. It just continued from where we left off and executed the second printout. So we can check if this is done now, and of course this is now done, so if I try to run it again, it will not work anymore. But a very cool and very essential concept here. So to sum up, virtual threads allow us to achieve pretty impressive efficiency. Creating virtual threads is cheap. You can have millions of them without the need for thread pools in most cases. Blocking is also cheap. You don't need more complicated asynchronous programming in many cases, you can just be synchronous. And if you want the flexibility of asynchronous programming, you can make it work with virtual threads through pluggable schedulers too. It should also be noted that migration to virtual threads is likely not going to be as scary as it might seem. We've seen some of the constructs in Loom that allow us to connect virtual threads to other existing constructs, but there's a lot more functionality in the JDK that has been adapted or will be adapted to work with this new model. This includes networking primitives like NIO channels, sockets, HTTP URL connection, console I/O, but DNS lookups, process pipes, and file I/O are also being explored. This means that many constructs that use these primitives, like JDBC drivers, HTTP clients, and servers, will get support for virtual threads automatically. And even frameworks and libraries external to the JDK, like Spring or Hibernate, ultimately delegate to the JDK when running blocking operations, so they will also get a lot of stuff for free. The expectation is certainly that the vast majority of libraries will not require any special treatment. And other JDK tools like debuggers and profilers like the flight recorder are also being adapted, and a lot of progress has already been made there. And that's it from me. I hope you found this talk useful. If you want to learn more about the topic, I'm sure you'll have no troubles finding materials on concurrency in general, but I thought it'd be useful to point out some resources about the emerging Project Loom, because these are actually not completely easy to find. The first link on this slide is sort of the main Project Loom resource. It's just a couple of pages on the OpenJDK wiki with links to downloads and such. But unfortunately, the documentation is very sparse. The closest thing we have to documentation is actually this article by Ron Pressler from the Java Platform Group on the state of Loom from earlier this year. This really helped me learn more about the project, and many of the examples I've shown today were inspired by these talks. If you have any questions, I believe we have a Zoom room arranged for the next 15 minutes. You're welcome to join, and I'll do my best to answer these questions. Or feel free to reach out to me later. My Twitter handle is in the corner here. And otherwise, thank you. Have a great weekend, wherever in the world you are, and enjoy the final keynotes here at Devoxx.